This video is on shear stress theory. Now, what is shear force and shear stress? You already know from strength of material. Now, there are three types of shear stresses. One is flexure shear, that is what you see in beam, it's called one-way shear. Another is punching shear, which is two-way shear, which you deal with in design of footings. We'll be doing it in this course. And another is torsional shear. If you remember from strength of material course, torsion gives the shear. But in this course, in this lecture, we are more concentrating on flexural shear. Okay, that is shear what you get in the beam from the shear force diagram. Now, main thing what you have to understand is what is nominal shear. That is, at any section where you want to design a shear reinforcement, at that point tau v, the nominal shear, will be shear force given by the shear force diagram divided by b into d, the dimension of the beam, where d is effective depth. Now, code gives this formula for tau c. What is tau c? Shear stress that can be taken by concrete. It is given by this formula, where tau c depends on beta, and beta in turn depends on pt, the percentage of steel. Now, this is shear stress that can be taken by concrete. Now, this, since the formula is complicated to work on, IS code also gives a table for a particular S by BD into 100, that is percentage steel for M20, M25, M30 concrete. You can, from this table, we can directly read out tau c. How much shear will be taken by the concrete? Tau c into area of the beam, that is BD. Okay. I would, however, prefer that you use the formula, because see here, if there is interpolation, then it is not linear and you could get into problems. Now, our main aim is to find for a given shear force the shear reinforcement. Now, you are going to find shear reinforcement for shear force not from the shear force diagram, but from VUS, where VUS is VU, shear force from the shear force diagram, minus VUC, the shear force that can be taken by concrete. And as I already said, VUC is tau c into B into D. Now, in order to take this, in order to design, we can have vertical stirrups, we can have inclined stirrups, or you can have bent up bars with stirrups. I'm going to concentrate only on vertical stirrups for the simple reason that I have not seen inclined stirrups at all anywhere. And bent up bars along with stirrups is a good practice. To my mind, it is a little dangerous, because if bars are not bent at the specified distance by any error, one could run into problems. So I would concentrate only on vertical stirrups. Now look at the diagram. The first stirrup starts 50 mm, as you can see from the diagram, from the support. And shear reinforcement, as you know, is in the form of a ring. And what you are required to do is find the ring spacing and the diameter. Ring spacing is SV. Now, a critical section for shear. Which shear force will you take from the shear force diagram? If beam is hanging, as in the lower figure, then shear, whatever shear force is at the support you take. But if beam is simply supported, then you take shear force at a distance D. See, that red line is at 45 degree. So at a distance D from the support, whatever shear force is there, that is critical shear force for the design. Now, code specifies that for a given grade of concrete, maximum shear stress can be this. I'll read out. For M20 is 2.8, M25 3.1, and M30 3.5. Unit is Newton per mm square. Now, the spacing of the stirrup, the formula is given by the code, and that is SV is 0.87 into Fy is the yield strength of the steel which is used for the stirrups. Usually it is mild steel, or sometimes it is taut steel also. Depending on that, you have to put Fy. ASV is the cross-sectional area of the stirrup, and you have to use twice that cross section because it is two-legged. So suppose I have 6 mm bar, then the ASV will be pi into 6 square by 4 into 2. D is the effective depth of the beam, and VUS is the shear force for which you are planning to design. Now, code specifies like this. That usually you use 6 mild, 8 or 10 torr bars. You don't use higher bars, 16, 20 and all that, because they are difficult to bend. And maximum spacing will be minimum of all these 1, 2, 3, 4, 5. Now when we do problem, we are going to do calculation, but just for information, SV just now I explained you, the spacing comes from the formula, or 0.75D, where 0.75 is the number and D is the effective depth of the beam, or width of the beam, or number 300, or 0.87 into Fy into SV upon 0.4B. Now the last formula, there is a star. What they say is when maximum shear stress is less than half the permissible value, what your permissible value is, what your tau c you get, then you need not apply the last formula. It will be more clear in the problem. So what it means is when shear force is very small, you don't need to use the last formula. So how do you design shear reinforcement? Very simple. You start with 6 mm bars and check all the spacing. If spacing is too close, then you go for 8 mm and give the spacing. When we are going to do all type of problems in the next video, and all these things will be very clear. Thank you.